So, few little remarks. First of all, there are two places you have to sign up. According to my observation, some people sign for one, not the other, and you probably, if you're one of those people, you want to reconcile the thing. You clearly want to get email, and you also need to be on the roster. The second thing, homework is important, not for me, not even for Diana, but for you. I mean, some of people came to me and said, well, I'm not sure HR will be checking on the homework, and well, I'm not convinced they will be checking on the homework. The problem we have, again, is that homework, I have absolutely no way to check 77 homeworks. I'll die. I'll die anyways, but I'll die sooner. So we came up with the following scheme, and the credit goes to Bill for the scheme. We are going to assign you randomly to a group. There will be 4 or 5 people in your group, and you have to become friends with them and check each other's homework and discuss it. Again, there is an important point which I'll be sort of discussing during the course time and time again, and many of you heard me saying it before. Science is a social activity. You have to discuss it with your friends. It's something good to talk about. So you will have to partner with your group, and in a second, I'll tell you how you determine your group. Notes and recording will be on the wiki, probably by the end of every Wednesday. Again, very strict, no laptops. People who brought laptops, put them under the chair, and please turn off your phones. I know that it sounds draconian, but that's how it is. I'm not going to justify it. You should be able to. It's a homework, number one. Justify the lack of the laptops. Office hours, I'll try to keep regular office hours twice a week. You're welcome to come. Do not hesitate to come. At least one Thursday in April, I will be away. I'll let you know. If you have questions, you could come and discuss them with me. If I'm not available, or if you're shy to discuss it with the Grandmaster himself, you could address helpers. There are 2 math helpers, Anil Gangoli and Tom London. So if you're not sure they understood some proof, or you're not sure that your proof works, they'll be happy to answer your questions. And there are 2 C++. Again, we're going to be using sort of almost empty subset of C++. But if you forgot how while statement works, John Kalb will be very happy to remind you. And Anil knows about if. So this is problem number 1. You have to do it. It's basically a hash function. You have to compute your hash function. You take your login ID, take ASCII codes, add them together, divide by 16, take the remainder. That's your group number. You go to the same page where you registered, and there is a place to put your group number. Put it there. Then other people in your group will connect with you, or you will connect with them. Should be pretty clear, yes? And we will also see how good is this hash function. Because if everybody goes into the same group, well, you have to do something about it. And it's fairly random. Again, Bill insists that we want to randomize the groups. And we might be randomizing them again and again. I'm not sure about that. For Journey. So what is this course? Again, it's sort of, some of you might have read what we announced. And let me tell you, I view myself as an ambassador who went on a long journey, met some very great people, and now I'm representing them. It's not that I'm great. I'm just this random guy who met Pythagoras and Euclid and Descartes and Leibniz and Euler and Cauchy, and I come back and want to share whatever they told me. And they told me many wonderful things. Again, I will try to present their message to within our sort of setting, the setting of modern programmers. I actually do believe, this is a belief which I held very firmly, that programming is a mathematical discipline. It is mathematics. I'll try to convince you of that. Some of you would ask, what kind of mathematics? And I'm sure many of you hear of all these new kind of mathematics. You know, Wolfram invented new mathematics. Dijkstra invented predicate transformers. This is sort of another new mathematics. There's linear logic, which is apparently, we'll explain. No, this is not mathematics I'm talking about. I'm talking about real mathematics, mathematics which has been around for thousands of years. Again, simple way of thinking of mathematics, it's arithmetic, algebra, and geometry, what you learned at school. This is still mathematics, that's the core. And I actually claim that this core, these things about numbers and shapes, and that's what I claim mathematics studies, numbers and shapes, are fascinating things. And it is a matter of, in some sense, faith. There are people now who says, well, I hate mathematics. We live in amazing times where a person could admit to hating mathematics, but they do. Even computer scientists tell me, I met computer scientists, sometimes distinguished computer scientists, who would say, well, mathematics is this hateful thing, has nothing to do with what we do. I disagree. I take an issue. I think mathematics is the core of what we have, is the core of our civilization. Precisely because it is, in some sense, is this wonderful language of the universe. Again, here I'm going to impress you with my knowledge of classical languages. And people have been saying something for millennia. What were they saying? That, as Plato says in the first quote, God always does geometry. And he's not talking about some mystagoguery. He's talking about very, very fundamental thing. The world is described by mathematics. Okay? The second quote is from Wisdom of Solomon. That's part of, at least sort of, for some denominations, their Bible. What does it say? The world is arranged by metro, arithmo, staphmo. What does it mean? Measure, number, and weight. Again, the number is the fundamental thing which arranges the world. Something is wonderful about numbers. And the final quote is very direct from Roger Bacon, a great English scientist, who says that you cannot understand anything without mathematics. Nothing. And I believe that. And again, I actually claim that it's a beautiful thing to know. It's a wonderful thing to know. And I want to, if you like, to remind you of that. I'm not claiming that I know more mathematics than you. For some of you, yes. But I know very little. Nobody could know all of mathematics. But it's a wonderful thing, and I want to sort of remind you of that and show that it does relate to what we do. So what do I want to do again? These are sort of my goals. That's how Dan will measure my performance. If I convince you that there are deep connections between programming and mathematics, teach you to recognize some fundamental abstractions, and to write software according to that. But more fundamentally, again, ignoring my goals, I will be very successful if by the end of the course, some of you will go and buy, say, Euclid. Just say, the heck with it, I can spend $30 and buy Thomas Heath translation and commentary and study it. I'll know that I'm successful. Okay? So I want to get to a point where you would literally view mathematics not as something hateful, not something which you should avoid, by something you could invent your own $30. You don't have even to charge to Bill. Yeah, maybe Bill will buy Euclid. We never know. again, what I will try to do is to try to show, it's a difficult task to try to convince you that it's not boring, because you have been conditioned. This is our high school teachers and elementary school teachers and professors in college are very successful convincing you that mathematics is boring. So I have to break through that. And I decided that the only way I could do it is by showing it in historical context, because that's how it became alive to me. You know, I was trained by some of the greatest mathematicians in the world, but I didn't quite realize how wonderful it was till I started reading history, till I started reading original works. Since I discovered, say, works of Euler and started reading them, things started looking differently. They became alive. So, you know, I will attempt to do that. It's difficult. Again, this is sort of, be patient with me, because I need to combine three things: programming, mathematics, and history. So, tough. But let's see. Maybe I'll succeed. I apologize. So, and when we're going through history, I'm going to introduce people, because, again, right now they teach history in what they call scientific, therefore boring way. And I'll try to tell you about people who are making it. Sort of, because if you know these people, you could relate to them. And I also believe that it's important to pick your heroes. You know, if your hero is Bill Gates, you will collect lots of money, or at least attempt to do that. If your hero is Euler, you will try to understand how the world works. These are different set of heroes. And I want to introduce you to some heroes. Many of them are men. One of them is going to be a remarkable woman. We'll have to wait till the second journey to meet her. Sort of, I hope that you will learn to relate to them and view them as real thing. Then there is another thing. We always, when we write code, some of us argue, is it good code, bad code? Right? It's very important for us to learn to recognize beautiful code. And somebody comes, say, Ryan, looks at my code and say, it's ugly. Does it all the time. And what do I do? How do I answer? Why do we have this disagreement? And I have claimed that we have disagreement because we do not have the common base. We never learned, how do you learn what is beautiful? Not by sort of thinking, but looking at beautiful things. How do you learn what music is beautiful? Well, some of you attempt to do it by listening to Lady Gaga. Some attempt to do it by listening to well-tempered clavier. And different ways, different modes of appreciation arise. And I claim that mathematics provides us a way of appreciating beauty. Theorems are beautiful. Mathematical edifices created over the centuries are beautiful. And this sense of beauty is very important if you design a piece of software, because it's something large. And we have to develop our sense of beauty and use it to succeed in programming. Again, I claim this aesthetics is of fundamental importance for us to do something worthwhile. Well, you say, Alex is utterly mad. This is true. But there are other mad people which I want to show you. I want to tell you that many of even great leaders of this country shared my attitude. Okay? And very few people will argue that Lincoln was the greatest president this country ever had. And everybody, I hope, knows that he was not educated at all. He grew up, you know, in Midwest, sort of splitting rails, doing hard physical work, not knowing much. And then when he turned ripe old age of 35, somebody told him that his mind was not developed, which was true. And he decided to develop his mind. What did he do? I think the most fortunate thing happened. He decided that the way to develop his mind is to buy a used copy of Euclid, only 6 books. 13 books were not available at that time in the state of Illinois, so he bought an abridged version and started studying it till eventually, this is, by the way, a quote from his own autobiography, written in the third person. He studied it till he, humbly puts it, nearly mastered it. That is, till he could repeat any proof at any moment at night. He was studying it mostly at night, traveling on a circuit. He was a lawyer. He was sleeping in one bed with 3 or 4 other lawyers. At that time, it was considered to be all right to sleep. So, and all of them snoring. True. I mean, and when they start snoring, he will light a candle and study Euclid. He clearly made a great president. And why did he study Euclid? Again, according to his own words, to develop his logic and language. Again, an ability to think logically and then present your thinking. And I actually claim it is. So that's what it does. I could bring many, sort of a plethora of witnesses to that. But these are 2 people who, Lincoln and Jefferson, which I will use here. Jefferson, of course, a sort of very different case from Lincoln. Well-educated from youth, sort of classically educated. Again, older he becomes, more and more he abandons reading of newspapers, political tracts, Declaration of Independence, all that stuff. And what does he read? He reads Euclid. How do we know? Because when he's quite old, he writes to John Adams, with whom he became first good friend, then the worst enemy, and then good friend. The story of Jefferson and Adams needs to be studied. It's very, very instructive. But he writes to him that I have given up newspapers and read Euclid and find myself much happier. There is an important lesson there. First of all, he already read Euclid as a child. Yes? So why again? And that is thing which I hear time and time again. I give speeches like that occasionally, and people listen and say, oh, very inspiring. I'm going home and I make my children study math. You understand what I'm objecting to. It's not about our children, whether we have them or not. It's about us. Jefferson was not making up his children to read Euclid. He was reading Euclid himself. He was not too old. He was not, again, another thing which happens in the modern world, I encounter it time and time again, that people decide, I already learned everything. I took a math class. Yes, I'm sure all of us did. But it's a prevalent. I had a neighbor once who went to Berkeley. And we were talking about classical music. And he says, oh, I don't need to listen to it. I took a course. He took a 1 semester course at Berkeley. He's done with music. No more. And that's what, again, mathematics is something wonderful. It's not for your children. It's for you. Sort of, again, it's. And in case of, again, Jefferson, he was very insistent. He actually maintained that no student should be admitted to the University of Virginia till he masters Euclid. And it's not easy. If you ever look at Euclid, it's not like geometry, which they taught you. It's serious mathematics with a great plan, great beauty. And sort of another amazing point, which I have to make, is what happened to the country. Apparently, Lincoln was using geometrical proofs during Lincoln-Douglas debate. Could you imagine now a presidential debate with references to geometrical proofs? I cannot. I would love to see them. But so, in any case, I'm just trying to say that mathematics goes beyond just what mathematicians do. right? I think that everybody, whatever their station in life might be, whatever their sort of calling might be, would benefit from mathematics. It's a wonderful, wonderful thing. Okay. There is no text for the course, which is very, very unfortunate, because it would be much easier for me to teach if there were one. There is a book which is an auxiliary text. The book with the same goal in mind, which Paul McJones over there and I wrote. You might want to use it as an auxiliary text. It's not required, but some of you might find it helpful. You could read it in any of these languages if you like. I have a couple of dozen extra copies in my office, which I'll be happy to give to those of you who do not. I mean, of course, all the best people, I'm sure, already have a copy. In any case, like Bill. He does too. I gave him. Again, it's not necessary. It's not a requirement. Right? So what is the difference between this course and the book? The book, Elements of Programming, attempts to do a classical, if you like, Euclidean presentation of material. Starts from the first things and builds it up. It was a wonderful accomplishment, especially since, you know, the idea of doing it was not my idea, but Paul's idea. You know, we're proud of it. Are we proud of it, Paul? We are proud of it. We think, I mean, in some sense, at some point in life, you realize that it doesn't matter what other people think, you know. And I know that, you know, it's just good for me to have this book. It doesn't matter if anyone will ever read it. And well, Ryan read it, so at least one more person read it. Many people bought it, but there's very little evidence that they read it. Again, a lot of the fundamental idea that sort of programming is mathematical discipline is the same in this course, but this course is going to be more historically based, again, entertaining, you know, I hope, and different. The book is there, and in some sense, the deep understanding could come only from carefully reading this book 3 times and doing every single problem and proving every single lemma, right? Sort of, if you aspire to really deep understanding, the book is the thing. Okay, so as you already heard, it's a journey-based course. There is going to be 4 journeys, I hope. I reserve the right to make 5 journeys if I decide to go. And the journeys are related to one fundamental algorithm, and then showing you how its history and how it is used in programming and everywhere. Right? So simple way to remember these journeys, there are very, very good names for them when you look at the page. I'm very proud of the names. And they also, you're supposed to laugh when you read them, but if you don't, you're not getting the joke. The simple way of thinking of the journey is the first journey, we're going to be doing multiplication. The second journey, we're going to be doing division with remainder. The third journey, we're going to be doing long addition. And the fourth journey, we will learn to add 1. So in some sense, it's a backwards. So these are very, very simple. You say, Alex, we learned it in the grade school. That's the beauty of it. What I'm going to show is the things which you learned in grade school are actually wonderful. Right, so the first journey is called Spoils of the Egyptians. And you are supposed to figure out why it is. I'll tell you at the end of the journey. And it is about things like commutativity and associativity, and how it is all very, very helpful for us in our daily activities. You've seen this, I'm sure. You've seen that a plus b is equal to b plus a, and a plus b plus c is a plus b plus c. And the same for multiplication. People observed it long, long time ago. These are self-evident propositions, as it were. But shouldn't we prove them? Isn't mathematicians supposed to prove everything they use? No. People have been quite happy relying on these things without proof for centuries. You see, the first, what we believe, rigorous proof of associativity of addition comes about in 1861, when obscure high school teacher of mathematics published a remarkable book where he proves some fundamental properties. We will be talking about during the fourth journey. By the way, everybody ignores it. The entire mathematical community says, what could a high school teacher know about mathematics? So his book is ignored, and it takes another almost 30 years till finally rigorous proof of associativity becomes the part of mathematical law. But people were using associativity for thousands of years prior to that. So we have to wake up once and for all and realize that proving is good, discovery is better. That is, the most important thing is to discover this truth, to discover that addition is associative. And moreover, sort of we have to figure out how to prove things. For example, why proving associativity of addition might be tricky. It's actually fairly easy to prove. Okay, let me go. Let me follow my slides. I apologize. There's some method in my madness. So Greeks realized that you could use spatial reasoning to prove algebraic facts. So let us look at the first proof, which appeals to our geometric reasoning. Of course, you learned in the 5th grade that a plus b squared is a squared plus 2ab plus b squared. Did you? Even rhymed it. So. That's how Greeks proved it. Okay, this is a geometric proof, which is in some sense wonderful. You know, my heart becomes warm. You know, my spine is tingled by some invisible force when I see these proofs. And so I could open parentheses there, I could do multiplication. It's not instructive, but here it is very instructive. You see two squares, you see two rectangles. Then if you think about it, these two rectangles are equal, because you could just turn them like so, and they will be the same. And you get our wonderful, wonderful formula. So this is a geometric proof of an algebraic thing. We'll be doing it during the first journey. We'll be doing a little bit of that. So we could even do commutativity of addition. It's sort of self-evident when you look at it. But it's not really a proof. It's an appeal to our intuition. Or associativity of addition. Again, another appeal to our intuition. We will do formal proof before we are done with the course. Commutativity of multiplication, that might be really a proof. Believe it or not, this proof appears in a great book by Peter Eugène Dirichlet, who was a very great modern mathematician, lived in the 19th century, when he wants to prove commutativity of multiplication. He actually says, let's arrange soldiers in a formation, and whether we count them by rows or by columns, the number will be the same. That's the argument. A pretty good argument, you know. So, and associativity of multiplication again, seems to be easily provable geometrically. We take this prism and we cut it. And we say if we cut it like so or like so, the volume will be identical. If you think about it, it literally gives us associativity. You have to think about it. Now, there is another wonderful geometric proof. You know, obviously you say, well, it's obvious that pi is greater than 3 because it's 3.14 blah, blah, blah. Well, but you don't know that. You see, you have to prove that it is something. So let us see how could you easily prove that pi is greater than 3. This is again the proof known to the Greeks and known to some other mathematics. We will talk about alternative mathematics in a few minutes. Sort of, if we take this, we obviously see that we could inscribe a heptagon, means 6-sided regular polygon, into this thing. And it's self-evident that its perimeter is smaller than the circle. Why is it self-evident? What are we relying upon? Shortest path. Yes, very good. We're relying on the fact that at least between these 2 points, the shortest path is going along the heptagon, not going along the circle. And if it's true for one side, guess what? It's going to be for 6 sides. And by the way, what do we know about if the radius of circle is 1, what do we know about the side of the heptagon? It's 1. So, you know, what we know is that the perimeter of this hexagon is 6. Therefore, the circumference of the circle, thank you, is greater than 6, which means that pi is less than 3. Greater than 3. Look, you will become old too. Okay, here we come to homework problems. And these are good problems. I really, you know, if I were you, I would do them. I did them, okay? And I wasn't even you. Okay, try, these are simple things which you, I mean, it will be all on the website. You don't need to write them. So these are simple things which you learned at some point in your life. So the question is, prove them geometrically. Find a geometric way of proving them. And even more importantly, try to use geometry for the following thing. Sum of first n positive integers. You might know the formula. And you might even know how to prove it by induction. But it's not what I'm asking you to do. I'm asking you to find a geometric, visible proof. So you could show it to your aunt, and she will say, aha, right? Because she could see geometry. And then finally, we found the lower bound for pi. Try to find simple, geometrically based upper bound for pi. It's very similar, very similar. It's not hard. By the way, if I'm going to give you a very hard problem, I'm going to warn you. By default, problems are simple. So here we get to an important point which I need to discuss. You see, we observed that people were using associativity without having its proof. And over the last several decades, we got into a lot of heated arguments. What is the proof? Proving problems correct, and whatever. And many young people, they decided that to prove something correct, you have to have this special program which takes something, goes crank, 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 and says, proved. This is false. Because let me tell you, if you ask me to take a flight on an airplane, which was designed and then proven correctly by this program, crank, 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 good, I'm not going to buy the tickets. I do not trust the program. I have absolutely no faith in it, even if it's written by very clever people. Or, let me be honest, especially if it's written by very clever people. So, I actually claim, and more I learn about history of mathematics, more I understand that we're talking about a long social activity when people sort of gradually accept things as proven, as true. It's a social activity. It's a process, right? And we have to be, when we want to know that some program is good, we want our program to be part of this social process. Without social process, there is no validation of correctness. That's some people might say, aha, he's talking about open source. No, open source is a tiny little part of it, and it's not even relevant in great degree, because there is no serious scientific effort there. I'm talking about we have to have a social process which sort of establishes validity of things. And an assignment. On the website, you will find a paper which was very controversial, and many of my friends will stop talking to me after they find out that I told you to read it. But you see how brave I am. I'm willing to risk it on your behalf. In 1979, 3 people, Rich DeMilla, Richard Lipton, and Alan Perlis, wrote a paper which just, in many words, say what I just said. That it is a social process, that mechanical theorem proving is not the path. It's not the way. By the way, you have to also, it would be good for you to know at least some of these names, in particular the last name, Alan Perlis. Sort of one of the founders of American computer science. American represent one of 3 Americans on Algol 60 committee, and the founder of computer science department at CMU, then at Yale, and a overall great man, a very, very sort of important figure. Some of you, of course, heard of Lipton, who is one of the top living algorithms guy. He's a youngster, unlike Alan, who is not a youngster, and sadly enough, long dead. But it's a very important paper. Read it. I will occasionally give you things to read because it's just good. It's not a difficult paper. Okay. Number systems. It's a remarkable fact that there is no civilization without mathematics. And I actually claim it's because I'm going to make a loaded political statement. There is no civilization without taxes. If you don't have taxes, I know there are many libertarians now, and you don't believe that, but historical fact, no taxation, no civilization. So, to tax, you have to have mathematics. Every civilized society developed mathematics. Every civilized society, these are 2 marks of civilized society, taxes and calendar. People know how to count time. You say, but couldn't you be happy without it? Yeah, you could. But is it the happiness you want? Is it what you want to? Is the life a hunter-gatherer the life which you want for yourself? That's your choice. But, I actually don't want to be a hunter-gatherer. I think that taxes are good, calendars are good. And finally, mathematics is good. So it appears in many places roughly at the same time. maybe say 5,000 years ago. We don't have any written records from 5,000 years ago, but one could argue fairly convincingly that about 5,000 years ago, in multiple places, mathematics develops. And there are even some interesting facts that sort of later on we will encounter a person called Bertel van der Waarden, who is a very, very important mathematician. But toward the sort of when he became old, I think when he turned like 40, he spent most of his research doing history of mathematics. And he actually discovered that there are similar computations of Pythagorean triples. Pythagorean triple is 3 integers such that the squares of the first 2 are equal to square of the third. The most significant, the one to remember, the one on which everything is found, is 3, 4, 5. Right, sort of, this is the most important mathematical discovery of all time. And apparently, it appears in a whole bunch of unrelated places. It appears in Babylonia, and appears in China, it appears in India. So van der Waarden actually claims that there is a common Neolithic source. And this mathematical knowledge spreads throughout the world from this common source. I do not believe that. Again, this is, I have enormous regard for van der Waarden. He was a very great mathematician, very great scholar. But I think there is a parallel evolution, as it were. You know, it was discovered, at least the fundamental mathematics seems to be discovered, and I'm not talking from first principles. I do not see how Inca mathematics could be connected geographically with Chinese mathematics. It's just, to construct a scenario is too hard. So it's much easier for me to accept that there is something innate which makes that when people start to organize things, they discover mathematics. But that's very important. This again, I claim that there is some innate ability. You do not have to learn it from your father. You have a chance of discovering it. It doesn't mean that most people discover it. Maybe 5 people ever discovered it, but you know, it could be discovered. There is absolutely, at least van der Waarden, when he was writing it, had absolutely no genetic data. The genetic data about the spread of human race is about 30 years after his publication. So it's clearly he was talking. Again, I have the book. If you stop by, we could discuss it at length. So now I have a great regard for different cultures. But I am going to tell you the story of what you would call European mathematics. And you could say, well, it's because you don't like Indians, or you are this white supremacist. No, I'm not a white supremacist. And but I have to tell you the following amazing fact, that the only living mathematics which survived, is European mathematics. When Ramanujan, a great Indian mathematician, wanted to do mathematics, where did he go? He had to go over the waters, which for him, as you know, was a huge big problem. He was a Tamil Brahmin, and at that time, traveling over the waters was a big, big deal. So he goes over the waters to England, to Hardy and Littlewood, because there is no Indian mathematical tradition he could relate to. There were very great people in China. There were very great people in India, but the tradition did not develop. Again, there is sort of great Chinese Liu Hui, who's sort of, I love mathematics, and let me tell you something. I shouldn't be telling you. It's about me. I also love poetry. And he composed one of the most beautiful mathematical poems, maybe the most beautiful mathematical poem ever, about his desperation of not being able to find a formula for the volume of the sphere. Sort of, you know, he was sort of slightly younger than Archimedes. Archimedes succeeded, he failed. He didn't know about Archimedes, but he was desperate and wrote this beautiful sort of poem. I don't know how beautiful in Chinese, it's probably so much more beautiful, but even in translation, it is very poetic and wonderful thing. So there were great people, and people we should know about and read their poems. But again, the story I'm going to be telling you is going to be history of European mathematical tradition, which actually eventually develops into computer science. You know, people like von Neumann and Turing were the product of this tradition. You know, and we are, whether we like it or not, we belong to that genetic line. Not genetically, but intellectually. There should be such thing as intellectual genetics. One of the younger people should start such a discipline. Sort of how. But I'm always looking at Ryan. Notice it. I have high hopes. So at this point, we're going to have a break.